Hello everyone, I hope you are doing well. My name is Wicket New, you can also call me Avon, and I'm currently a research fellow at the Department of Electronic and Electrical Engineering, University College London. At UCL, I work closely with Professor Kai-Kit Wong on fluid antenna system, and thus in this tutorial, I will talk about channel model. Okay, so this is the outline of my tutorial. Firstly, I will talk about the key factors in fluid antenna system models. After that, I will introduce you to several existing channel models, such as classical channel model, generalized channel model, 2D fluid antenna surface channel model, and finite scattering channel models. In addition, it's also very important to note that there are many other channel models in fluid antenna system. So what I'll do here is that I will briefly discuss uh, the unique features of some of the existing channel models, and you may refer to relevant papers for more comprehensive treatment. Okay, so at the end of this tutorial, I hope that you will know some of the key factors that shapes the system model. Furthermore, I believe that you'll be able to model the channel fast in Matlab and also identify the advantages and disadvantages of different fast models. Okay, so let us begin this tutorial by discussing the key factors in fast models. So in the system model, it is very important to consider the implementation context. For example, if the fluid antenna is implemented at the receiver side, then we need to consider the spatial correlation at the receiver. And this because the preset locations of the radiating elements or ports in fluid antenna system can be arbitrarily close to each other. Okay, and conversely, if the transmitter is equipped with a fluid antenna, then the spatial correlation at the transmitter becomes crucial. Next, we need to focus on the fluid antenna structures. For example, whether the fluid antenna has one-dimensional, two-dimensional, or even three-dimensional surface. And what is the size of the surface per dimension? Like this is usually measured in terms of wavelength or lambda. How many preset locations or ports are there in each dimension? And fluid antenna may have single or multiple active radiating elements, which are also referred to as active ports. So the latter may actually also necessitate other considerations such as mutual coupling effects. In addition, it's very important to also contemplate the communication environment. For instance, whether the area surrounding the transmitter and the receiver are rich or finite in scatterers, and whether the transmitter and receiver have line of sight or non-line of sight. So these factors here would inherently shapes the system model. So in the following, I will introduce you to several existing channel models. Specifically, I will highlight the assumptions behind these channel models and also discuss the pros and cons and also teach you how to model these channels in Matlab. So let us begin with the classical channel model. So in this channel model, it is assumed that the fluid antenna is implemented at the receiver side. Okay, so this fluid antenna is one-dimensional surface. It has one-dimensional surface. And in this surface, it has N ports. And these ports are evenly distributed over the length of W lambda, where lambda here is the wavelength of the carrier frequency. Furthermore, it has an active ports or one active radiating element. And thus you can see that the parameters in fast are N and W. Okay. The environment in this model is 2D and it has rich scattering effect. Now, the spatial correlation of the endpoint can be modeled using this equation here, where J0 is the zero order Bessel function of the first kind. The channel between the receiver and a single traditional antenna transmitter can be modeled using a channel vector H, where the first entry can be modeled using a complex Gaussian random variable with zero mean and unit variance. And this means that x1 and y1 here are real Gaussian random variable with zero mean and variance of 1/2. Hn can be computed using this equation here for all n larger than 1. And as you can see in this equation, the nth entry is coupled with the first entry only, which also referred to as the reference part. So this actually makes the model and the performance analysis much more tractable. Okay, but it also imposes a constraint on the covariance, and thus it might lead to overly optimistic performance. Okay, so we can use the Matlab code here to model the classical channel. So note that this code here only generates a generalization. Okay, so W and N here are the fluid antenna parameters. X and Y here are real Gaussian random variable with zero means and a variance of 1/2. H1, mu n, and Hn can be computed using the equation shown in the previous slide. Okay. Now, if you are very good in Matlab, you can also model the channel using vectorized method, and this can help you speed up the computation very quickly, especially when you consider a large number of generalization, right? But in this tutorial, I will mainly use a for loop for the ease of exposition. Okay. Next, we'll discuss about the generalized channel model. So this channel model is based on the same assumption as the classical channel model, but it is proposed so that the covariance will follow the Jack's assumption. So how to do that? Well, to do that, we can first define the covariance matrix of H as J, where the NM entry of J can be computed using this equation here. Okay. Now, since J is a symmetric matrix, we can factorize J using the eigenvalue decomposition, and thus we have J equals to Q times lambda Q conjugate transpose. And with the eigenvalue decomposition, we can model the channel using this equation here, that is Q times square root of lambda times G, where G here is a circularly symmetric complex Gaussian random vectors. So this will make the covariance of H as G, right? Alternatively, we can rewrite the n entry of H as this equation. Okay, so the advantage of this channel model is that the spatial correlations follows the Jack's assumption, that is J, right? But it's very difficult to analyze the performance of fast using this model because, as you can see in this expression, all the random variables are now coupled together. Okay. So this is the code example for generalized channel model. Similarly, we have the fluid antenna parameters, and then we can compute the NM entry of J. After that, we can obtain the eigenvalue decomposition, and we'll be able to generate the channel using this equation here, where G is the circular symmetric complex Gaussian random vector, right? Okay, so the generalized channel model can also be further extended to the 2D fluid antenna surface channel model. So the key difference in this model is that the fluid antenna surface now has two dimensions. So each dimension has a specific length and a specific total number of parts, as shown in this figure here, actually. So because we consider a 2D fluid antenna surface, it's necessary to consider a 3D environment. And in this model, a rich scattering environment is considered. Furthermore, the fluid antenna can be implemented at the transmitter side or receiver side, or even at both ends. All right? So the spatial correlation can be computed using this matrix here. To compute this matrix, we need a mapping function to map the 2D indices to 1D indices, the part of the indices, I mean. And then the NM entry of J can be computed using this equation here. Now, because we consider a 3D environment, so we need to compute the zero-order spherical Bessel function here, or the sinc function, okay? So with the spatial correlation matrix, we can now model the channel, okay? So the channel can be computed using this equation here. To the left of G, this is related to the spatial correlation at the receiver side. And to the right of G is related to the spatial correlation at the transmitter side. And G here is a circularly symmetric complex Gaussian random matrix. Okay, so what's the advantage of this model? The advantage of this model is that it has a 2D fluid antenna surface, right? It has a 3D, it considers 3D environments. And the fluid antenna can be implemented at either side or both sides. And thus, the performance of FAST can actually be improved, right? Nevertheless, the drawback of this model is that the rows and columns of H are now fully correlated. And thus, it can be very challenging to analyze the performance of FAST using this model. Okay, so this is the example for 2D fluid antenna surface channel model. So this quote assumes that the parameter at the transmitter and receiver sides are the same. Now, because we consider a 2D fluid antenna surface, so we have W1 and W2. This gives us W. And similarly, we have N1 and N2. This leads to N. Then we need the mapping function to map the indices. And with that, we can calculate the distance of the parts. So if the distance is non-zero, we can compute the NM entry of J using the zero-order spherical Bessel function or the sinc function. But when the distance is zero, the sinc function can be undefined. So in this case, we can actually use the limit to compute the NM entry of J, right? And then the codes below are similar to the generalized channel model, except that now we need to consider spatial correlation at the receiver side and the spatial correlation at the transmitter side. And furthermore, G is a matrix here. Okay. Lastly, we'll talk about the finite scattering channel model, and I believe this would be one of the most general channel model that we'll discuss in this tutorial. So compared to the previous channel model, this channel model further consider line of sight and also the finite scattering effects. Now, in this channel model, the spatial correlation can be considered using the steering vector here. Okay, and then the channel model can be computed using this equation here, where K here represents the rise factor. Omega here represents the line of sight phase. And then L is the capital L here is the total number of non-line of sight path. And this kappa L is the complex coefficient of the L non-line of sight path. Okay, and the advantage of this channel model is that it's much more general and also accurate. But the disadvantage is that there are actually quite limited statistical information. And thus, what I notice is that most of this channel model are usually used for optimization or evaluating the performance of FAST. Okay, so this is the example for finite scattering channel model. We have the environment parameters, fluid antenna parameters. Then we have the line of sight phase, azimuth and elevation angle. Then we have the steering vector. So this is the channel for line of sight, and this part here is for the non-line of sight channel. Okay, and this gives us the overall channel. Lastly, it's worth noting that there are many other existing channel models. Okay, for example, the spatial correlation can actually be modeled using the couplet theory, as shown in this reference paper here. So this is actually a mathematical approach to model the spatial correlation, and the advantage of this model is that it provides several flexibilities. And then the correlation can also take place in time and frequency domain in addition to the spatial domain. Furthermore, the movement of the radiating elements can also be modeled as a continuous function, as shown in reference 4 here. Now, when multiple pods are activated, it will actually create the mutual coupling effect. So this mutual coupling effect can also be incorporated into the channel. Okay, and then the pods can be distributed in a way similar to uniform linear array, uniform planar array, or even circular array, as shown in this reference here. Furthermore, all the channel models that we have previously discussed, they can also be extended to the scenarios with multiple transmitter and receivers. Okay, so with that, I would like to end this tutorial. If you'd like to know more about fluid antenna system, you can also visit this website here. And thank you, and I hope you enjoy this session with me.